Welcome back. You've done the hard work. You've crushed the gate, you've architected the phases, and you've filtered out the noise. Your sample is pure. But we have a final, frustrating problem. You have the needle, but it's buried in a liter of solvent. Your analyte is so dilute, it's like a whisper from 3 miles away. Have you ever felt that sinking feeling when you look at a beautiful, clear extract and realize your target is at part per trillion levels? This is where we use the signal booster. Concentration is the volume knob of sample prep. Today, we are going to learn how to turn up that gain without burning the sample or letting the truth evaporate into thin air. Purification is only half the battle. If your target is at trace levels, it simply won't trigger a signal on the mass spectrometer unless it's concentrated. Think of it as a signal-to-noise challenge. Even if we've removed the noise, proteins, lipids, the signal itself is still too quiet. We need to physically reduce the volume of solvent to force the analytes closer together. This is a high-stakes operation, because every time you evaporate solvent, you risk losing the very thing you're trying to keep. Speed is the enemy of recovery here. We must respect the vapor pressure. To master the signal booster, we categorize our techniques into 4 strategic pillars. First, end-tube blowing, the gentle wind of surface evaporation. Second, SpeedVac, the high-throughput vacuum vortex. Third, we'll identify the silent killers, like total dryness and adsorption. Finally, we'll master the recovery audit using internal standards as our GPS. This roadmap ensures we move from the macro view of signal gain down to the microphysics of molecular recovery. An operator just wants it fast. A specialist wants it right. Most technicians think nitrogen blowing is just about blowing air on a liquid, but a specialist understands it as a battle of vapor-liquid equilibrium. By sweeping away the saturated air layer directly above the sample, we drop the partial vapor pressure to nearly zero. This forces solvent molecules to jump into the gas phase much faster. It's a precision mass transport operation. But we must be careful with mass transport. Too much speed leads to turbulence and loss. It's about moving the molecules out without losing the signal in the splash. Here is the specialist's secret, the dimple. When you aim that nitrogen needle correctly, you create a slight depression in the liquid. This physically increases the surface area, more exits for the solvent to escape. But be careful. An operator turns the gas up to max to go faster. A specialist knows that too much flow causes splashing, the #1 cause of cross-contamination, and excessive evaporative cooling. If you see droplets jumping into neighboring tubes, your signal booster has become a signal destroyer. Because evaporation is an endothermic process, it literally freezes your sample as it works. If the tube gets too cold, evaporation stops. We use a water bath or dry block to feed energy back into the system. But remember, heat is a double-edged sword. If you cook your sample, you're not concentrating your analyte, you're destroying it. We want it warm, not boiling. A specialist monitors the temperature as closely as the nitrogen flow rate. If you burn the sample, all the purification work you did earlier becomes meaningless. Now we move to the gold standard for high throughput, the SpeedVac. While nitrogen blowing is great for a few tubes, a specialist needs a system that can handle 96 samples at once without cross-contamination. The SpeedVac is an elegant solution to a messy problem. It uses a vacuum to pull molecules out by changing the physical properties of the environment. But to do this safely, we must use the marriage of 2 physical forces. If we use vacuum alone, the sample boils over. We need a counterforce to keep the truth at the bottom of the tube. The SpeedVac operates on the principle of combining centrifugal force, vacuum, and heat. The vacuum reduces the internal chamber pressure, which significantly lowers the boiling point of the solvent. This allows solvents to evaporate at much lower temperatures, protecting heat-sensitive samples like DNA or proteins. The centrifugal force is the hero here. By spinning the samples at moderate speeds, we create a downward force that suppresses the formation of bubbles and prevents violent bumping. This ensures the solute is deposited as a neat pellet at the bottom of the tube for nearly 100% recovery. The G-force vortex shield is critical. It eliminates the bumping or sudden boiling over that ruins samples in a standard vacuum oven. In clinical proteomics or drug metabolism studies, where you have 96 well plates, the SpeedVac is your best friend, because it eliminates cross-contamination between tubes almost entirely. You aren't just an operator. You are a workflow architect managing a vacuum system. This stability is what allows us to set the machine and walk away, assuming we've accounted for the silent killers. We need to talk about the most dangerous moment in the lab, the transition to total dryness. For many technicians, dry means finished. To a specialist, dryness is death. When a sample goes completely dry, your delicate analytes are no longer protected by a solvent layer. They become exposed to the harsh realities of physics and chemistry on the glass surface. This is where you lose your signal forever, even if the instrument is working perfectly. Let's look at why going to dryness is the ultimate technician's trap. Have you ever found zero recovery and blamed the instrument, only to realize you accidentally blew your sample away? This is adsorption. Your molecules stick to the silanol groups on the glass wall like glue. Or worse, if the heat is still on, they undergo thermal breakdown because they've lost the heat sink of the solvent. The pro move: never go to 100% dryness if you can avoid it. Stop at 50 microliters, or kick the sample back into solution immediately with your mobile phase. If you let it sit dry for an hour, the needle isn't in the haystack anymore, it's welded to the floor. Let's summarize the choice. N2 blowing is fast for single tubes, and great for very volatile solvents like hexane. SpeedVac is the king of throughput, and handles bumping-prone solvents with ease. But both require you to respect the vapor pressure. If you push too hard, you'll lose the very needle you spent all day trying to find. Choose the tool that matches your matrix and your deadline. Actually, most modern labs use both N2 for quick turnaround and SpeedVac for the heavy-duty clinical workloads. We've turned up the volume. You now know the physics of the dimple, the stability of the centrifugal vortex, and why dryness is death. If you remember only one thing from this briefing, let it be this: speed is the enemy of recovery. If you try to force the molecules into a signal booster too fast, they will simply vanish into the exhaust fan. Respect the physics, use your internal standard to audit your work, and the mass spec will finally be able to hear the whisper you worked so hard to find. You've boosted the signal. Your sample is concentrated and pure. But there is one final wall. Some molecules simply refuse to turn into gas. They are too polar, too heavy, or too stubborn for GC per megasiemens. To make them fly, we need to perform chemical surgery. Join me in our next unit, Module 2-9, Making Molecules Fly, where we master derivatization to force complex compounds into the gas phase. We've found the needle. Now let's make it reach the finish line. I'll see you in the next mission.